Hello, everyone. Welcome to this session where we're going to talk for the next 45 minutes about service mesh. What is service mesh? Do we ever need it? What advantages it comes with? What headaches and problems it brings as well? And before jumping into the technical discussion, I want to start by sharing a little bit of a story, and especially the story of the phone. So following the invention of the phone by Graham Bell, the first phones were primarily point-to-point communications, and which limited the communication only between the parties that were operating at both ends of the instruments. And that was obviously not scalable. So in order to scale, some sort of interconnection was necessary. And for that, we invented what we call switchboard, and we hired switchboard operators. And the job for those switchboard operators was basically to route traffic manually to their final destinations. And that says if I want to call someone, I would pick the phone, not to call the person I want to talk to, but actually to call an operator and ask them to forward me to the person I want to talk to. And the further the call I want to make, the more switchboard operators I had to talk to. But even with that, we didn't manage to scale really well. More phones meant we need to invent and build more switchboards, and we needed to hire more switchboard operators. And the solution was we needed to move away from the manual aspects of human interfacing to a more automatic and digital exchange where everything is routed automatically. And you may be wondering right about now, while we're talking about the phone in the middle of a technical conference. And the answer is, I believe that we kind of follow in the same way in the way we build, architect, and deploy our applications. We started with monolith, simple flow of communications, and in order to scale, we started to break the monolith down into smaller and smaller services, making the communication and handling the communications between those services a lot more challenging. So the 30 seconds ads. Ciao a tutti, I am Mohammed. I work at Spotify as a backend engineer, and my Twitter handle is Laytoon. And if you want to discuss anything Java-related, cloud native, or anything in between, please feel free to reach out. I'll be also in the conference, so if you want to discuss anything, let's grab a coffee. And let's actually analyze the journey of how we architected our application in the past 30, 25 years or so. In the 90s, this is how the majority of our application looks like. Simple flow of communication, all the components tightly packaged together in this one single deployable, and simple flow of communication, as I managed, between the client and the server. However, if you want to scale, you're going to start to have some problems, and it's going to probably hit you hard. So in order to scale, we started to break the monolith down into smaller services, and we invented what we call the service-oriented architecture. And some means of interconnection was necessary. And for that, we used MQs and enterprise service buses. And the communication between services was either to pass simple data or to collaborate to achieve some sort of functionality. And ESBs reigned back in the days as to the preferred way to interconnect service-oriented architecture. And the promise that enterprise service buses comes with back in the days was actually legit. And if you read those lines, it looks like some of the things that we're trying to actually achieve with the newest technology that is cropping up. However, the amount of enterprise service buses, if you have worked with them, you know that they are actually hard to operationalize. They are notoriously hard to operationalize since it was comprised of multiple deployment units, which made the collaboration and automation really challenging. And no one picked ESBs back in the day for agility or ease of use, but it looked like as the right solution back in the days, since we had different sorts of challenges. But yeah, nevertheless, moving on. And in 2010, it was about making everything smaller. We moved it toward dump pipes, decentralized communications, and we started to spawn multiple services to build our applications. And it did actually scale. You probably heard it in this conference, in another conference, read in a blog post in a book, or a podcast, whatever. You heard some of the companies that managed to run hundreds of micros or hundreds of services, and they scaled really well using this type of architecture. But there are some issues even with this architecture. Let's consider this small, typical service mesh architecture. And you have two services in the top. I don't know if you can see them, but let's consider this service X and this service Y. And then service Y become unhealthy. And service X depends on service Y on some of its functionality. And service X keeps calling service Y incapable of handling errors returned by service. Service X keeps calling service Y incapable of handling errors that were returned by service Y. And that leads to increase of CPU usage and a decrease of number of the available threads, which led to service X becoming healthy as well. And the same thing happened to the services that rely on service X. And the issue which propagated through your whole cluster and all your services. And you probably know this already, and this is what we call a cascading failure. And this is how we look as developers, engineers, ops operators, trying to figure things out. As once we move it toward a decentralized communication, turning off and on the server doesn't work anymore. And the thing is, distributed systems follows Murphy's Law, which says that anything that can go wrong will basically go wrong. The more instances of anything you have, the more the likelihood that one of them will break, probably all of them. There are things that the monolithic architecture guaranteed that are no longer true when we move it toward those loosely coupled distributed architecture. Services no longer stop and start in a predictable order or in the same time. Services can change their state, their version, stop, start. Like, there are a lot of things that can go wrong in a distributed system. If there were no errors, microservices and distributed systems will be easy, but this is not the case. And this is not new. More than 20 years back, James Gosling, the father of Java, and Peter Duce defined what we call the 8 fallacies of distributed systems. And those are the things that we as developers or the people in the IT industry believe, and they are actually false assumptions. So let's have a look quickly over them one by one. We tend to think that the network is reliable, and this is not true. There are a lot of things that can go wrong in the network. DDoS attacks, update failures, patch failures, network congestion, a lot of things that can go wrong in the network. So the network is definitely not reliable. We tend to think that the latency is 0, and there are 7 orders of magnitude differences between a code that is made in memory and a code that is made over the network. So the latency is definitely not 0. We tend to think that the bandwidth is infinite. And nowadays, this is generally not an issue. However, even if the bandwidth has significantly increased, the amount of data we send over the network has increased as well. So we need to be mindful about the bandwidth as well. We tend to think that the network is secure. And this is the fallacy that gets a lot of media coverage, unfortunately. So unless you want to appear in the news the next day, unfortunately, not for the good reason, you need to make sure that your application is actually secure. We tend to think that the topology doesn't change, and this is not true, especially in the era of cloud-native microservices and containers. We need some degree of elasticity and agility in the way we build our architectures. We tend to think that there is one administrator. This is obvious, not true. There is no one person that knows it all. We tend to think that the transport cost is 0, and anyone here who saw the cloud bill from your cloud provider by the end of the month know that this is not true. Know that the transport has a cost, and it can be expensive at some point. We tend to think that the network is homogeneous. And this is not true. We have no control over what network and path the requests follow to reach our service and back to the client. More than that, there are other things that make and other challenges that appeared when we move it toward those loosely coupled distributed components. Observing interactions and communication between those services become now more challenging and more hard to get right. Traffic management and doing things like A/B testing, canary deployment, especially without affecting users and clients, become now more hard to do right. Securing communication and encrypting the flows that is circulating inside your cluster becomes really challenging, especially when we have different binaries that are probably written in different languages. And finally, managing communication failures and timeouts and issues like the cascaded failure that we discussed earlier becomes really hard when we move it to distributed systems and microservices. So the thing is, when you consider how critical is the ability to control and monitor service-to-service communication that relies on network calls in each and every transaction, you understand that we are kind of under-tooled and why having more than a few services is actually really hard. But as I mentioned before, those issues are not new, and we had them before, and we tried to solve them by following different paths. And we tried to solve them using the message brokers, and we had this set of messaging-oriented middlewares, and we tried to add infrastructure concerns like retries, service discovery, back pressure, and so on and so forth to the message broker. However, this option turned out to be quite a bottleneck, and we ended with bloat, and it was quite heavy-handed to operationalize. Then we said, we have this enterprise service bus that was responsible of, connecting the services and passing data around. And we said, let's add those infrastructure concerns, things like retries, rate limiting, and so on and so forth to the enterprise service bus. However, enterprise service buses, as I mentioned before, was, before quite heavy and quite hard and notoriously hard to operationalize. Adding those features made the amount of collaboration and coordination needed for the deployment crazy. And we figured out that started to mix application logic or business logic with infrastructure concerns, which, it's actually not a good idea. And with the rise with the API first mindset and the risk evolution, we invented a new piece of software architecture, which is the API gateways. And API gateways enable us to manage access to our business APIs through business quotas, documentation, and so on. And it's great, it works. However, we still didn't solve the problem of the intra-cluster communication, which is like, because since the API gateway operates out of bound, like at the outside perimeter, and control the access to our cluster, we still didn't manage how we can handle the communication inside our cluster, which we call the east-west traffic. And we also started to follow kind of the same path with the ESPs. We started to mix business logic with infrastructure concerns. And the solution that many companies that adopted microservices followed is basically to use client libraries. And the solution here is we started to develop like client libraries that handle those infrastructure concerns and network features, things like service discovery, circuit breaking, timeouts, and so on, and have a single deployable that contains our business logic and those client libraries, and deploy that to our cluster. And it did really work. However, it requires a significant amount of investment in a single language or runtime. And also, as you can see, it's like we are mixing also application concerns or application infrastructure concerns with business logic. And those client libraries, especially if you have a system that is already running, can be really costly to wedge into your existing infrastructure and needs to either rewrite your whole application, move to the cloud, and yada, yada, yada. Nevertheless, moving on. And the next logical step same as what happened with the phone, is to take those infrastructure concerns and move them down a layer to where they belong, to the network, to the infrastructure. So if you think about it for a bit, wouldn't it be awesome if we can control and monitor those infrastructure concerns without the need to manage client libraries or write the code that do that? And implementing this idea was look something like this one. We would only focus on writing business logic. However, we will have a separate layer in the network, in the infrastructure that handle all the network features that highly scalable distributed system needs. However, implementing this idea is not actually feasible since the network is already defined. And yeah, there is no way we can change the network layers. The good news is that this idea wasn't completely abandoned. And it was implemented following the sidecar pattern, which means that we will insert transparently a new piece of infrastructure, which is the sidecar proxy, which transparently adds the desired features, things like service discovery, circuit breaking, retries, timeout, and so on. And the traffic and the services will no longer call their downstream dependencies directly. However, the traffic will go first through this sidecar proxy, which adds the desired features. And this is how the service mesh was born. So the service mesh is not an introduction of new functionality, but rather a shift from where the functionality is located. It doesn't establish connectivity between the services, but have policies and control that augments and monitor how the communication in your service, on your communication of service to service communication. And as I mentioned before, service mesh shift the responsibilities out of your application and put it down a layer to the infrastructure. So you will focus now on writing business logic, fixing bugs, introducing new features, and you will have this dedicated piece of software infrastructure that do the heavy lifting, giving you, in turn, the ability to control it and monitor your services. And this is great in a sense, as microservices enabled our team to move to more cross-functional, general purpose teams. Service mesh, the promise here is to decouple operators from development release process, giving them, in turn, as I mentioned, the tools to control and monitor how the services inside your mesh interact. And as we're moving in the cloud-native era to a declarative way of handling our infrastructure, you can think of service mesh as a programmable framework that allows you to observe, secure, and connect your infrastructure, meaning that you declare your intentions in, whatever that file, YAML probably, and good luck with that. And the management layer will basically take those intentions and apply them to your cluster. And the promise here is to make the communication between your services more flexible, reliable, and fast. And this is a helicopter overview of how a typical service mesh deployment will look like. Since the traffic is going first to the sidecar proxy, we end up with a deployment architecture that looks like an array of lightweight proxies. Traffic is first redirected to the proxies, and the proxy lives next to each service, the application instance, and the application is completely unaware of their existence. And a typical service mesh architecture contains two planes, the data plane and the control plane. The data plane are basically the sidecar proxies. Whether the traffic is entering or leaving your cluster, the proxies add the desired feature and goes first through the sidecar proxy. So it manages the intra-cluster communication as well as the inbound, which is the ingress gateway, and outbound, which is the outbound traffic. The control plane is the management layer of the service mesh, taking a set of isolated proxies and turning them into a service mesh. It has policies and control over the services it controls over the mesh. And this is an important thing to keep in mind. If it doesn't have a control plane, it ain't a service mesh. Do not confuse a service mesh with a mesh of services. A service mesh is the management layer that has defined policies and controls. That's how your services will interact. And the mesh of services is all the services that enable your application to perform its functions and do its tasks. And you may be wondering right about now, didn't we solve this already with containers and container orchestration tools like Kubernetes, right? And the quick answer is no. And the long answer is still no. And containers provides generic non-language specific packaging and lifecycle management for your packaging lifecycle management for your application. And container orchestration tools like Kubernetes are generic non-language specific platform that takes care of many things. Resources scheduling, handling high-level abstract components like deployments, services, and so on and so forth. However, service mesh are Service mesh are a dedicated layer that adds the missing service level needs that highly distributed application needs, such as circuit breaking, canary deployment, retries, back pressure, and so on and so forth. So this table highlights core capabilities of orchestration tools like Kubernetes and what the service mesh tries to bring to the table. And it's not about microservices only. Non-distributed monolithic application will stay around for a long time. And the promise of service mesh is it will help in modernizing those infrastructure without the need to rewrite your whole application and onboarding your legacy application into the mesh. However, keep in mind that the more services you have, the greater the benefit of using service mesh. And this is a quick overview of the service mesh ecosystem. You might be already familiar with what we call the big three, SEO, Linkerd, and Console, but there are many other frameworks and tools and partners that are pushing the boundaries of what we can achieve through service mesh. And quick overview over what service mesh features are. And we can split them into four major components. The first one is traffic management. And service mesh offers a dazzling array of features in regard on how you want to route traffic inside your cluster. Things like canary deployment, A/B testing, routing based on some metadata, user header, user ID, browser, whatever you can set in the header, you can route traffic based on it. Resiliency features include rate limiting, fault injection, circuit breaking. Those are all supported in the service mesh, and you can declare your intention, as I mentioned, and the management layer will take care of applying those definitions and those policies into your cluster. Security. With service mesh, you can define policies of how services can call other services and which service is allowed to call other services, giving you in turn the possibility to define more and policies that allows better policies. And most service mesh architecture or solutions have a certificate authority that manages certificate. And adding to that the mutual TLS, you can encrypt the traffic that is circulating inside your cluster out to both parties. So mutual TLS, it's like TLS, but it's in both parties. So both services are clients and servers. And one of my favorite features of service mesh is observability. And observability can be in forms of logs as errors or events, metrics, in the forms of histogram, gauges, and counters, and traces in the form of annotations and spans. And it's time for some fun. It's demo time. It's gonna be a live demo. I'm not sure if you can scan the QR code there. It's gonna bring you to a website. Full disclosure here, I tried this demo 2 times, and it failed in both times. So crossing fingers this time. Done? Okay. So you should see this super amazing sock shop, right? Feel free to create an account, check the catalog, order some socks. Everything should be fine, right? And this is deployed in a Kubernetes cluster, GKE in the cloud, and they have 2 namespaces. Can you see it? People in the back, can you see the locks? Thumbs down, thumbs up, thumbs down? No? You can see the automation increase. How about now? Good, cool. So I have 2 namespaces. This one in the bottom is basically Istio installation. It contains Istio stuff. We have the core logic, which contains different components, the egress gateway, which is like the one that controls the traffic going out, and the ingress gateway, the traffic that's coming in, and they have observability stuff. Jaeger, Kiali, Prometheus, Grafana at some point. And I have another namespace, which is called SockShop, this one, which contains my applications. It's basically a microservice application that contains a lot of services that are written in different languages. We have Python, Node.js, Java, Go at some point, I think. And it looks like this. But yeah, it's different components. We will come back to it. And let's start with observability features. So we have Grafana here, out of the box. You define it, and hello. We have Istio, and we have a lot of dashboards. Let me increase this a bit. We have a lot of dashboards. Istio stuff, and we can go to the service dashboard. Yeah, you can see how your application is performing, the traffic you get. It basically provides out-of-the-box black box monitoring. You don't need to do anything. You basically need to install Grafana and all those observability features, and you get all of that out of the box. It basically inject and inspect the traffic and send it to Prometheus, which is like the backend at time series database. You get monitoring out of the box with Service Mesh. Prometheus, it's basically, time series database that have a lot of metrics about everything that goes inside your cluster. Jaeger, if you are lucky, it's debugging microservices is hard, and Jaeger enables you to trace how the request, the flow of your request inside your application. And if I'm lucky, we can check something here. Yes, so yeah, those are spans, and you can trust like the flow the request follow it, or the flow of the execution of the request. And this is really important in tracing latencies, for example. If you have a service that is behaving really slow, or a request that is really slow, you can track it and spot where the latency is, or the bottleneck in your flow of your request. And Kiali here is basically an Istio dashboard. It provides a lot of insight about your cluster. And this is how the application actually looks like. Oops. No? 0? Can I increase this a bit? Yeah. So we have multiple components. There are some failures in there. Is the application still running? Yes, it is. Yeah, but that's fine. So this was a quick overview over the observability feature. I forgot to mention that this internet, hello, I am connected, yes. This is open source, and you can basically go to, where is my, nevertheless, repos. Where's my repos? Okay, Service Mesh. Yes, this one. It's open source. It's a self-walkthrough tutorial. that you can use. It doesn't need the cloud. You can basically install Minikube, Docker. Now that comes Docker Desktop. It has its own Kubernetes cluster, and you can install it and you can play with service mesh installation, especially this one is SCU. So we have a lot of things. Traffic management, resiliency policy. It's a full 2-3 hours workshop, self-workthrough that you can follow. Now, let's have some fun. So what I'm going to do is, let's do some traffic management stuff. So if you can check here, I have 2 versions of the front end. I have the front end application, and we have a second version of it. But now we are only accessing the one application, the first version. So what I'm going to do is I will do some blue-green deployment. Okay, deployment. This is deployed. Where it is, where it is, where it is. Mirroring, blah, blah, blah. Let's do some blue-green deployment. I want to route traffic to virtual service 2. And what it will basically do, so I have a virtual service here. Virtual service is basically where do you want to route the traffic inside your cluster. And the destination rule is once the traffic is routed and it reaches its destination, what I want to do with it. So if now you refresh your application, you hopefully will get the new version, which is the red version. So both applications are still deployed side by side, V1 and V2, and the only difference is like the top bar, it's blue in the V1 and red in the V2. However, I managed to do blue-green deployment. And this is really good in case of failures in the V2 version. I can quickly roll back by a single command to my previous application and restore the functionality of my service. I can do other things, which I can do canary deployment. And that means I will redirect 80% of the traffic to the V1 and 80% only to the V2. Following the same pattern, I'm going to copy that one. And now, if that gets deployed, hopefully, what will happen is 80% of the time I'm going to hit the V1 version. However, if you keep refreshing, you will hit at some point the V2. And this is great if you want to do, if you have like, you want to test your releases. You don't want to like release it to 100%. You want to release it to some specific set of users until you check how your application is behaving and gain confidence over the new release. Then you can roll it out to more users. There are a lot of things that we can do as well. Resiliency feature. One thing I wanted to mention, probably in the resiliency feature, is how we can introduce failures. Josh Long, which is an amazing friend and speaker, probably was here before in the conference, says that the perfect or the amazing place on earth is production, and this is where your user goes. So if you want to do some experiments and especially test resiliency of your application, you need to actually do it in production. So let's actually do some fun and try to introduce some issues. Let me go there up a little bit, sorry. Fault injection. And for fault injection, I'm going to try to introduce some delays. Wait a minute. Nope, is it? Delay. Yes. So what I'm doing here is I'm going to introduce a delay in the catalog service. It's under resiliency, fault injection, and delay. So I'm going to introduce some delay in the catalog service. So I'm going to introduce the 5 seconds delay. This is great if you want to check how you're going to perform when a service starts to respond slowly. And there, if I refresh, you're going to see that the service is now becoming slow to return the catalogs. After 5 seconds, then your catalog is going to pop up. You can go crazy here. You can return errors, kill the whole application, and check how your application is performing. So this was a quick overview of some of the service mesh features. But the repo, as I mentioned, is open source. Please go there, have fun, and enjoy some SEO capabilities. And then come the question, that this whole application was built upon. Do I need a service mesh? Think about it. If you really think that you need a service mesh, then think twice. I would not recommend it, but yeah, there are some cases where service mesh makes more sense. Starting with modernizing your existing infrastructure. As I mentioned before, monolith application and legacy application will stay around for a long time. The promise of service mesh is it can help with their modernization. It basically can provide facets to onboard those legacy applications to the mesh. Another use case is service sprawl. If you have a set of microservices, but you don't know how well those services are actually doing, using service mesh observability features can help you to understand how your application is actually performing. Another thing is monolith to service migration. If you have a big monolith and you want to start split it down into multiple services, or you want to pull a functionality out from a monolith into its own application, you can benefit from service mesh traffic management features. You can test your application, allow only certain users to route traffic to the new service, do some testing, and then when you are sure, transparently route traffic to the new service. And if things goes wrong, then you can route traffic back to its original component. Another use case is if you have release bottlenecks, if you don't trust the release process of your services, then you can benefit also from the traffic management features of service mesh. You can shadow load, you can mirror traffic and check how your application is performing. You can allow only a specific set of users based on request metadata. And then when you gain confidence, you can gradually roll it out. Start by 0.5%, 1%, and then gradually roll the traffic out to reach more users until you get confidence over your released application. Another use case is debugging microservices. Microservices is really hard to debug. Some of us certainly spent days or even weeks trying to understand a weird bug that it's happened once in a while. The promise here is using service mesh observability feature can help you to gain an understanding over how your application and cluster is doing. And finally, chaos engineering. The best place on earth is production, is where your users go. And if there's an issue, it's gonna happen there. So using service mesh, resiliency feature, fault injection, error injection, you can test how your application is, how resilient your application is. You can start small. You can introduce delays and then grow gradually and limit traffic probably to your whole application and check how resilient your application is. And this is a great graph from Nginx, which basically says, as the complexity of your microservices grows, service mesh becomes a more realistic approach to service, implementing feature service to service. And as the maturity of the system and service mesh architecture grows, the tipping point of adopting microservices will go down, basically. Another great set of graphs from Kinvolk, we did a benchmarking between deploying an application in bare metal compared deploying it with SCU and Linkerd. And what they found is those services add some latency and some issues, and they are not free. So this one shows some latency increase. Second one shows the memory usage compared to, this is the bare metal, and this is with the service, the sidecar proxy, and in the CPU utilization. So service mesh is not free, and it comes with cost. And think also about the cost, not only the cost of memory usage and CPU, but also think about the environment drift. We took a component out of the application and put it down into the infrastructure. This is great, offer great possibilities. However, rolling back if things goes wrong can be costly, at sometimes impossible. So this is an investment that you need to make. Another investment is the learning curve. It's new technology, relatively new technology now, and your team and yourself as well need to take time to understand the technology, play with it, hurt yourself, shoot yourself in the foot until you understand the technology and stabilize it. So there is other cost than the resources. And that's pretty much it. So yeah, as I mentioned, quick overview, service mesh. The promise here is to allow to observe, secure, and connect microservices. It's a new technology implementing old patterns, basically shifting where the implementation responsibility lives. Hopefully, the promise is it brings value for both monolith and microservices. And my advice, if you want to start exploring with service mesh, it's start small and grow gradually. And with that, a lot of resources. The resources demo is mentioned here. I'm going to share the presentation afterwards, and a couple of links that helped me to build this presentation and has some great insights also about what service mesh is. And thank you.